Okay, so good evening, everybody, and welcome to lecture two. We were off to a great start on the other day, and it's nice to see a lot of people for today's lecture. Today, Professor Goswami, after half an hour, will break for 15 minutes or so people can unmute themselves and ask questions. And we are requesting that people ask questions directly on the topic itself, on what is being covered in the lecture itself. Otherwise, what happens is that we go too far away, and many people who don't understand something in the lecture don't get an opportunity to ask questions. So at that time, you'll be able to unmute yourself after the first half an hour. Professor Goswami.
Thank you very much, Rama. Thank you very much again, and welcome everybody. Okay, so today we are going to talk about the driver and maintenance of the mean climate and how it is connected to complexity. In the last lecture, we essentially talked about we discussed the three-dimensional structure of the atmosphere in terms of winds and temperature and humidity and precipitation, etc. And one of the things that was most important question was why the winds are easterly in the tropics and equatorial region and westerly in the extratropics. So this has been is an important question for general circulation and climate. And today we are going to try to understand what produces these winds. The winds are generally formed by pressure gradients. So if there is a high pressure area and there is a low pressure area, the winds will blow from high pressure to low pressure, and that's how the winds are formed. But how are the pressure gradients produced? The pressure gradients are produced by essentially heating gradients. So if there is a heating, a column of air is heated, it becomes lighter. So the pressure over below that becomes lower. And in a region where it is cooled, the air becomes heavier and the pressure below it becomes higher. So this is how the surface pressure gradients of the low and the upper atmosphere, the pressure gradients could be reversed because it just expands or contracts the column. So the pressure gradients are produced by heating gradients. So fundamentally, the winds are caused by heating gradients. So where does the heating gradients come from? The heating gradients essentially is a result of the radiation balance from the sun and the geometry of the Earth-Sun system that produces the distribution of heating over the Earth. And of course, all of you know this geometry of the Earth. I'm not going to spend a lot of time, but because of the inclination of the axis on the ecliptic plane, the distribution of the sun rays at different latitude becomes different, and that that is what is going to determine what is the heating over tropics and that over the polar region, and we will come to that. And so that is going to be our the first part of the lecture today. And so how does this produces the heating sun rays? The solar radiation comes in, then it goes through the atmosphere, and part of it gets reflected back from the clouds, the aerosols, the vegetation, and then part from the surface, the ice, snow, etc., etc. So a fraction of the total solar radiation that comes in gets reflected back to space. So only the incoming minus the reflected is what is received at the surface of the Earth. Now, once it is received, the Earth gets heated up. Then the Earth also radiates like a black body. So when the Earth radiates like a black body, it radiates at a long wavelength, and we will discuss this in a minute. And these waves, the radiated energy from the Earth, then tries to go to the space. Now, that radiation being long wave, a large fraction of that radiation get absorbed in the atmosphere due to different constituents in the atmosphere, and a fraction of that then finally leaves to the space. So a balance between incoming solar radiation and outgoing long wave radiation is what makes the temperature that is means the net radiation balance at the surface, and that net radiation balance will increase or decrease the temperature. So that is how it is going to heat or cool. Now, to understand that, we have to understand a little bit about the black body radiation. You know, there are several. I'm sure everybody knows, so I'm not going to spend a whole lot of time. So we know the Planck's law, which gives us the distribution of the radiation as a function of wavelength and this energy. And then there is this Poincare displacement law, which tells us that any black body, the maximum radiation radiated by a black body, the wavelength at which the maximum radiation is radiated by black body is inversely proportional to its temperature, and that is given by this relationship. This is important because that is what determines the amount, the wavelength at which the most energy is there. Then, of course, the black body radiation is given by the Stephen Boltzmann law, which is the 10 to the power 4 law. And so these three laws are very important and to understand. Now, with this, you can see what happens to the radiation that comes in and how the radiation from the Earth, the solar radiation, I mean the Earth's radiation can go to the space or get lost to the space. So here is the spectrum of sun's radiation. This is sun's black body temperature is close to about 6,000 degrees, and therefore, therefore it's according to Poincare law, this is around, maximum is around 0.5 micron. This is our visible range. On the other hand, the Earth's radiation, the mean temperature at the top of the atmosphere is what it is going to be radiate with, and at the top of the atmosphere, the Earth's temperature at the top is defined as where there is no the density, the greenhouse gases are very little. There is, so everything that is radiated is lost to space from that point and that point. So, so that is about 15-16 kilometers. So at that point, the temperature is 255 degrees Kelvin, and at that temperature it will radiate. So okay, and that temperature, the maximum of that will be around long waves. It's about 15 micron. So so it varies from about 3 micron to about 50 microns. So of course, from lower region, the temperature is high at the surface, is about 300 degrees or more sometimes. So it is somewhere in that range. In this wavelength range only it will be there, and so that long wave radiation will also try to go up into the space, and therefore the part of that will be absorbed depending on the absorption bands in the atmosphere. So the absorption bands are shown here. So in this region, there is very little absorption bands in the atmosphere. So the solar energy, most of the major part of the solar energy just goes through like a glass, because there is no absorbing material for that so towards the long wave range, there are few absorption bands, and they come from water vapor and carbon dioxide, and they do absorb a little bit, not a whole lot. But therefore, the most part of solar energy just comes in. A very little is absorbed in the atmosphere. On the other hand, the Earth's energy is radiated in this spectral band, and there are a lot of absorption bands. For example, this infrared, there are so many absorption bands coming from carbon dioxide and water vapor. This region is slightly less. There are a few, and here at the surface, the ground level, at the upper atmosphere, there are a few, but the ground level there is a lot. So whatever is coming from ground actually gets absorbed in the atmosphere, between the top of the atmosphere and the. So therefore, a large part of Earth's radiation is absorbed within the atmosphere. And then of course towards the far infrared, there is a lot of water vapor continuum, and that actually really kills everything. So therefore, a whole large fraction of the energy coming out of Earth actually gets absorbed into the atmosphere, and this is essentially the basis for the greenhouse effect. So solar energy comes in, which is it goes like a glass house. It goes through most of it, then it hits up the Earth, and then Earth then radiates at a long wave, and the long wave cannot go out. Therefore, the amount of energy lost to the space is much less than the energy that comes in from this. Therefore, the temperature will start increasing, and temperature must increase to a level where the lost energy fraction of that temperature for which the lost energy to space will be equal to the energy received at the surface. That is what is the greenhouse effect, and that is how the balance of radiation will take place, and that balance of radiation will determine the temperature. And this can be represented in a very simple energy balance model. And this energy balance model, and we just assume that Earth is a sphere. It's a very simple, it's basically 12 standard pixel here. So suppose you have the Earth is a sphere, and a solar energy comes in, and the solar constant is the amount of solar energy per unit area that is coming on. The Earth has a radius r, so a disk of r pi r square will intercept that energy. Okay, so pi r square intercept that energy, but a fraction of that energy gets reflected, alpha fraction, which is called the albedo. That is the fraction that is reflected back. So 1 minus alpha into S naught, and pi r square is the amount of energy that it receives. So on the other hand, Earth is a spherical object, and it radiates all around, and therefore it radiates to the Stefan-Boltzmann law, sigma t to the power 4, but it radiates over the whole spherical surface, and that 4 pi r square into sigma t to the power 4 is the amount it radiates. But all of it does not get radiated out to space. Only a fraction of that gets radiated out to space. That tau fraction is the atmospheric transmissivity, long wave transmissivity. Only that fraction is get lost to the space. So that's amount of energy lost to the space now balances the amount of energy coming to the surface, and therefore that determines the surface temperature. So this is the basic equation. So here are the three factors that can influence our equilibrium temperature. So one is of course the albedo. Albedo is nothing. Albedo comes from clouds, vegetation, land ocean distribution, and so many other things. So that is one important part. So if the albedo changes, like today we are changing the sea ice, for example, or the ice in the polar cap is decreasing. So these will affect the albedo, and the change of albedo will affect the incoming solar radiation. Then that will require a different temperature to balance. So temperature will change. On the other hand, solar energy itself can change, and that solar energy has in the long due to the geometric effect of this sun, the astronomical parameters like it's the eclipse, the orbit, changes in the orbit, changes in this the eccentricity, and changes in the axis at which the angle at which it makes the axis makes with the ecliptic plane. All these will change the amount of energy, solar energy that comes into the surface. So solar energy can change through various reasons, but that time scale is very slow. On the other hand, this transmissivity of the long wave radiation depends on the greenhouse gases in the atmosphere, the water vapor, the carbon dioxide, methane, and so on. So these gases are very unique to the atmosphere, and that has its unique greenhouse gas, greenhouse effect. So with this, if we just try to calculate what is the equilibrium temperature, so you balance these two terms. Suppose I assume that the transmissivity, there is no atmosphere, and the infrared transmissivity is just 1. That means everything that is radiated from surface gets lost to the space. So therefore, and then I use the albedo as approximately the observed albedo is about 30%. Solar constant is about 1365 watts per meter square. You put those numbers and you get equilibrium temperature, which is 255 degrees. What I had shown you at the top of the atmosphere. And that is exactly what happens. So if there is no atmosphere, at the top of the atmosphere, the temperature will be balanced by everything that is lost there to the space and whatever the solar energy coming in, and get and the part that is reflected minus the part that is reflected back. So if that was the case, then the surface temperature would have been minus 18 degrees Celsius, and it will have been completely ice covered. The whole globe would have been ice covered, and then life would not exist. So therefore, the basic constituents of the atmosphere and the distribution of the constituents, the concentrations, distribution of the different concentrations of different gases in the atmosphere, it is dominated by nitrogen and oxygen, and that basically is why they don't have in that visible range, there is no absorption. On the other hand, it has carbon dioxide and water vapor. That is why it has absorption in the longer wavelengths, and this is uniquely creates a greenhouse effect in the atmosphere, which is of the order of about 33 degrees. The observed temperature, surface temperature is about 288 degrees, and that means about 33 degrees warming has taken place due to the greenhouse gases in the atmosphere. This is a natural greenhouse gases. Now, the anthropogenic greenhouse gases is just on addition to these. Suppose I go back to pre-industrial area, our only change will be basically the carbon dioxide and methane. And at that point, so from that point today, we have increased both carbon dioxide and methane. That has increased decreased the infrared transmissivity. Therefore, it will increase the surface temperature by another delta T, and that delta T may be about 2 to 4 degrees if we double the carbon dioxide. So that is the kind of simple calculation you can actually do from here. So with this, you can actually calculate, with this background, you can actually calculate all the temperatures of all the planets. And in fact, Venus is sort of closer to the sun, therefore the top of the atmosphere, this is represented by F here, not S0, but this is the same thing. So high energy it receives, but it has a huge albedo, 78%. And therefore, it reflects a lot of energy back, but the surface temperature is very high. That is because it is filled with high level of carbon dioxide atmosphere. So it is a very huge greenhouse effect, and that is why the surface temperature is very high. On the other hand, Mars is farther away. Its solar constant is smaller, but albedo is also very smaller. But still the surface temperature is pretty cold. But in fact, if you see the surface energy received here also is not very different from Mars, but the temperature is much higher because the greenhouse effect here is much smaller. That is because the atmosphere, Mars atmosphere is very thin, because look at the Venus's atmosphere. Venus's atmosphere is 90 atmosphere, 90 bars. If Earth is 1 bar, it will be 90, 100 times more, that much dense, and it is filled with carbon dioxide. On the other hand, Mars is 100 times smaller thinner than the atmosphere, our atmosphere. It is also having carbon dioxide, but it just have not enough concentration to produce the greenhouse effect that is required to warm this. So this is the kind of thing that we can actually understand from. So what is the role of the atmosphere? The role of the atmosphere is that it decreases long wave radiation lost to space, but it depends on the clouds, water vapor, and carbon dioxide distribution. Now, so okay, this is the same thing that I have already mentioned. Um, so, but now let us come back to the real situation. However, that was a very simple, model in which we are assuming that over the annual mean, over the whole globe, if I consider as whole globe as just one ball, then what would be its temperature? But actually, if the temperature is uniform over the whole globe, then there will be no motion because there will be no pressure gradient. And therefore, that is not what happens in reality. That is because the sphericity of the earth and the inclination of the axis to the ecliptic plane, radiation received varies with latitude, and that is the major reason for the climate of the earth as we see it. Now, you can look at that radiation, if we look at the radiation distribution, so there are three curves here. I'm showing the solar radiation that is on annual mean as a function of latitude, and also in summer and winter, JJA and DJF is summer and northern hemispheric summer and winter. So obviously, when there is northern hemispheric, this side is south and this side is north. Okay, so this is the annual mean is about 400 watts per meter. So let me concentrate on annual mean. The differences in the seasonal cycle you will understand once you understand this annual mean. So annual mean sense the about 400 watts per meter square you receive at the surface and at the tropics, and we about 170 or 75 watts per meter square you receive the polar region. But now reflected part is very interesting because on annual sense mean about 20%, about 100 watts per meter square is out of this 400, about 25% gets reflected back. In the polar region, this increases to about 125 watts per meter square on annual mean. But the variation during summer and winter in the polar regions is very large, very large. Okay, so reflected is not a very significantly different on annual mean. Now if I convert that as a percentage of the total energy that it receives, which is called the albedo, then it so happens that in this polar region, in the tropics, only 25% is reflected back at percentage of, because already you remember the energy received by sun at the polar region is 175 watts per meter square, but 125 of that is reflected back. So that is a large fraction compared to what we receive here, 400, and out of which 100 is reflected back. So that is what the albedo is, therefore very significantly different from tropics to the polar region, and that is a large very important for the heat balance. So it is about 25% here, it is like 70% there in the polar region. So that is a big difference. And on the long wave radiation side, how much is lost is so this is the upshot. The long wave radiation is here. So long wave radiation that is lost in the space in the tropics is about 250 watts per meter square. So we received about 400 and then the about 250 watts per meter square is lost. And 25% that 25% of that 400 is reflected, and the rest and this much is lost. So the difference is a positive balance of about 70 watts per meter square in the tropics, and in the polar region, on the other hand, it loses about 150 watts per meter square, the long wave radiation. You remember that it had only received 175 watts per meter square, out of which it is lost, reflected back about 125 watts per meter square, and now it radiated back about 130, 150 watts per meter square. So there is whole lot of radiation loss in the polar region. That is why if you take a balance, there is a negative balance in the polar region, about 100 watts per meter square. So that means it is cooling. So this is mainly because of large reflectivity as well as the long wave radiation loss. Why long wave radiation loss is more in the polar region? Because there is no very little moisture. You remember I showed you the moisture, the distribution. The moisture distribution indicates that because the temperature being very low, there is very little moisture in the atmosphere. If the moisture is a very strong, and the tropics we have a plenty of moisture, and because of this moisture actually acts as a very strong greenhouse gas, and it does not let a large fraction of the long wave radiation to escape, and that is why we have long wave radiation loss here is less. Comparatively, relatively less, and this is still is much more for their temperature. So as a result, what happens is essentially there is a positive balance of radiation in the tropics, which is varies up to between about 30 degrees plus minus 30 degrees, and there is a negative heat balance at the surface over the polar regions. And this is the main driver of our climate. And this is what is so. This is what is shown here as a schematic here, where this is actually the incoming solar radiation and the long wave solar, and this difference is the difference is the net. So there is a positive net heat balance at the top of the atmosphere and negative net heat balance at the polar region. Therefore, air must rise at the tropics and sink over the polar region, and that will produce, at least it is likely to produce one big sail going upward in the tropics, and then they going towards polar region and sinking, and then coming towards equatorial region as one big sail. So one large sail is possible, and that possibly could distribute some of the heat. But if that is so early attempts to explain the general circulation assume this as a single big sail, but it could not explain certain things like the easterly. So if suppose there was only, let me just show you. Sorry, suppose there is only one sail, then if this big sail, the air will go up and sink there and come down like this, and then the air will come at the lower level from the pole to the equator, and therefore it will produce, through the rotation of the earth, it will produce Coriolis force. It produce the easterlies. So there will be easterlies all over the place. Now, how do we explain the westerlies in the middle edge? So one big sail cannot explain the westerlies. Something else have to happen. So, but this is but this the another thing is that is one big issue. The other thing is that this heat energy, if it is continuous to goes like that, this on an annual mean sense, this is happening. That means it's always continuously heating up the tropics and cooling down the polar region. If this goes on, temperature will go on rising in the tropics and go on cooling in the polar region. But it's not happening. There is a balance. Now, how does that balance take place? That balance demands that the energy must be transported from tropics to the polar regions, and that can be by using just continuity. You can actually calculate at any given latitude how much energy must be transported across that latitude to maintain this balance. This can be calculated by this simple formula. This is the top of the. This is the difference between this FTA is the net heat at the balance at the top of the atmosphere, and that is the difference between this curve. And then from any latitude here, if I integrate it to the North Pole, then whatever balance is there at that particular latitude, if it is suppose there is a net positive balance here, that much energy must go to the south. So that much transport has to the circulation must transport that energy, that much energy to the south. So that is why the negative sign is there. So by that you can change the latitude and calculate how much energy has to be transported from each latitude, and that we can calculate. And I'll show you. And this happens due to the basically, so that difference in the heating in the tropics and the polar region and produces the pressure gradient. That pressure gradient then produces the winds. Winds are then moved around by Coriolis force. And of course, there is gravity and friction to essentially determine the final winds. So that is basically how it happens. So let me stop at this point. This is just exactly, so I'll open it up to questions. Anupam, you can go ahead.
Yes.
And so I request that the questions may remain sort of concentrated on the topic of this lecture.
Thank you. First question is from Professor Sandeep. Professor Sandeep, you can go ahead, please.
Yeah, thank you very much, first of all, Professor Goswami, for these lectures, which are really wonderful. And I want to thank you from all our behalf for all your effort and time. Thank you. I'm sorry, my questions will be very elementary. Please excuse me.
Thank you, no problem.
But just to go back to the beginning of your talk, you explained very nicely this, deficit that in a sense, had we not had any atmosphere, the temperature would have been much colder, but it's 33 degrees or so warmer than that 0th order estimate. And I was wondering, is there a similar back of the envelope kind of estimate which would give us that 33 degrees or something nearabouts? I think Rama in our discussions had perhaps once explained, I'm not sure, by taking one layer of atmosphere or something, can we do some rough order of magnitude? That was my first question, sorry.
It's essentially, you can do that. The only thing is that you have to, you essentially have to estimate this number, the infrared transmissivity. So how do I estimate the global infrared transmissivity? Now, if I know the global infrared, that is the back of the envelope calculation. All you need is, So this number, we need this. How much? This depends on the distribution of all the greenhouse gases, a concentration of greenhouse gases. So if we have a good idea of greenhouse gases, as a consider the air, atmosphere as a slab, and in that slab, if I put all the greenhouse gases amount, which all we know, and in fact that is how our old old physicists had made this calculation, how much we actually do. So if we know that, and how much water vapor is there in the atmosphere, because water vapor is also important. But water vapor is essentially the it's a variable quantity, but we have that mean distribution of water vapor. So we know that. So therefore you can make a calculation. There is no, it's very simple.
Okay.
But you need to have that an estimate of those concentrations.
I see.
So which is not impossible.
Okay.
That can be done.
I see. Okay. Thank you very much. And then my second very naive question, sorry if I'm permitted to ask by whoever is moderating. Is it okay? Just very quickly.
Yeah, please go ahead. Yeah.
Okay, thank you. So you explained, I sort of understood that, you have this excess in a sense over the equatorial region and this deficit in the polar region in terms of the energy which is going out versus what is coming in. And that means that the air would, being hotter, would rise up from the equatorial regions and come down in the polar regions.
Correct.
And then you said, okay, that won't explain the easterlies versus the westerlies. But just, if you don't mind, just if it were the Coriolis force, which is, if I remember, omega times V, right? Then wouldn't it mean if V is going upward in the tropics, that omega cross V would have one sign near the tropics, and if V is going downward near the polar regions, omega cross B would have, am I wrong? Sorry.
No. So what we are seeing is that that is correct locally, but basically we have to look at these winds that are coming, not going up or down at some place, but what is coming at the surface or at the upper atmosphere. At the surface, so there is wind is going up, but then moving away, moving to the polar region, and then so that wind, you will be seen from a reference point to be moving in a direction according to the Coriolis force, and the wind that is then sinking and coming towards equator at the surface will be opposite direction, and that opposite direction will be again seen in an opposite way due to the Coriolis force. And so therefore the surface winds, here I am just taking I am referring to only surface wind. This is only surface wind. So the surface wind part, if this wind is coming from the pole to the equator, it will look like it is moving from east to west, northeast to southwest. So this will look like this, and they will look everywhere because the winds are coming here all the way from polar region to the tropics. Everywhere it will look like easterlies, and that is the problem. So I'll explain as I go along how we can resolve this problem, and that we need something more. What we need more is a creep cells. Now, if I have an opposite another cell, for example, here, this one cell, this is called the Ferrel cell, which I had shown you in the last class. Then from observations, we know there is a descending motion around 30 degrees and an ascending motion here around 60 degrees. So this sail goes up at 60 degrees and comes down at 30 degrees north. And this sail, then the surface winds are now moving from equator to pole. Now, if surface winds are now moving from equator to the pole, Coriolis force will then push them to look like as westerlies. And that is what we see. So, but question then remains is, what produces this cell? And this cell is what we don't understand. We did not understand for a long time, and now we have a reasonably good handle on that.
I see. Okay. Very last, I'm sorry, I'll really stop, but have they observationally seen the presence of these cells?
Absolutely. So that was not very clear when we did not have good data. But today, now that we have good data, that is why in 50s and early 50s and 40s, there is a lot of debate about these cells, and we did not really have. But now today we have good data, three-dimensional data. Now we know that these three cells are reality, and that is, there is no doubt about that. And of course, but the point is that, you know, do that real observations are, the vertical velocity is not observed directly on the large scale. So you infer that from the horizontal motions and continuity, and but that is consistent.
I see. Thank you very much. Sorry.
Okay.
Please.
Okay.
Next question is
one or two quick questions we can.
Okay. Next is by STCS department. So please go ahead, STCS.
Yeah, no, I'm just logging in from this account. I'm still Sandeep. Sandeep. I had a very naive question. You know, if we want to have more albedo and more reflective, reflection of sunlight back is a good thing right now. Why don't we make all our construction, whether it's roads or roofs or any other thing, more reflective?
Well, that's a very good question, and that is a good suggestion, and people have been, this suggestion has been made, and I think it is applied also many places where the rooftops have been so concrete houses rooftops have been has been painted white or things like that. This can help a little bit, but there is a sort of the problem of our the global warming, the increasing the other greenhouse gases. Unless that is solved, I don't think we can really solve this. Engineeringly, what is called the engineering solution for the global warming, people have a lot of these ideas. Like suppose I put some things that will reflect the solar sunlight more, like putting some aerosols in the stratosphere, for example. Then those aerosols will reflect more, but then they will have other implications, chemical processes, and then the atmosphere will have different constitutional change, and therefore other effects will be there. So therefore, this is called geoengineering. So geoengineering, there is a whole lot of different spectrum of things that people are suggested, but I think we have not come up with anything that is sustainable and is cost effective. And that is also is an issue. But that possibility is there. But the main problem is that the scale at which we are decreasing the albedo by losing the ice, sea ice, is something that is going to be very difficult to replace by this kind of thing. So we need to stop those natural way of decreasing the albedo.
So is there anything promising at all in geoengineering that you see right now? Or?
Personally, I don't think so. Personally, I don't think so, because there is lot of different. I have my personal doubt about this, but that is debatable. There is a lot of debate on this, and there is of course a whole group of people who do think that there is some scope on geoengineering, but largely geoengineering is promoted by the oil lobby, and therefore because they have interest to continue the coal burning. So we don't want that. So I think we have to make a balance between continuing to increase the greenhouse gas and doing this kind of geoengineering to reduce the effect of global warming. So yeah, it's a very difficult question.
Okay.
I have my personal views that geoengineering is not going to solve our problem.
Not even partially, not even small amounts.
Yeah,
Okay.
yeah, because the scale is very large.
Scale is very large. Okay. Thank you so much. Yeah.
So, Professor Goswami, will take one last question.
One last question.
Okay.
Question. Yes.
Hardik Mehdi, please go ahead.
This guy would be so much more.
Yeah, please unmute and speak, Hardik. You are unmuted. Are you able to speak?
Hello.
So he's not able to speak. So I'll read out his question.
Okay, please go ahead.
So his question is, how do we calculate the value of albedo for a planet? And then he asks, what factors are taken into account for its calculation? Can we calculate albedo values of exoplanets?
That is a tough question. And for the planet, of course, there is it's not just one thing. We have so it's a very there is a lot of uncertainty. I mean, can come in making the global albedo estimate because it depends on several things. One is the reflectivity from the land itself. From different soils have different reflectivity. For example, desert region has a different reflectivity compared to a green region. The green region has a much less reflectivity, 20%. The desert may still be almost by 60%. So and that is variation. Then, so the vegetation is very distribution of vegetation. What kind of vegetation? Short grass, tall grass, or big trees have different. So all these things we do a sort of cumulative, a sort of rough estimate of these can be made based on the distribution of vegetation, land, ocean, and the ocean of course has 70% of it is ocean. So therefore the water has its own reflectivity. That's not very high, but the polar regions have a lot of snow covered. Mountains have snow covered. Snows have reflectivity of about 70% or more. And the polar regions have ice have reflectivity of 70% or more. So that the area covered by them will determine how much of that fraction will go to the global reflectivity. The area covered by different regions has to be sort of area weighted and their reflectivity will determine the actual estimate of reflectivity. So now this measure, this has been now, because satellites are there. Now on the top of the atmosphere, we have satellites, and satellites are measuring all this. This reflectivity can be very well measured, because now a satellite is going around and around, and so you know how much solar energy is they are receiving reflected energy. So this reflectivity has been satellites can do that. So there is a complexity in estimating the reflectivity, but so therefore the exoplanet I cannot predict anything. So in atmosphere we can definitely do it by different earlier estimates. Lot of data people collected, and they made an estimate. There are errors to balance this radiation budget, but now we are narrowing that errors by from satellite measurements, and of course more surface measurements and of different things. So I hope that answers your question roughly. The bottom line is that Earth's reflectivity now we can estimate reasonably well. There is no not much error, but in exoplanet will need all these different parameters that you need. But from some spectroscopic measurements, maybe some estimate can be made from there. Okay, I think I'll stop here from the question answer at this point of time. Then we'll continue. Okay.
Sure,
Okay.
sure.
Thank you. Okay. So basically now, our point is that this radiation balance does indicate that the energy can be transferred from tropics to the polar region by possibly one cell, air rising in the tropics and sinking over the polar regions and coming towards equator from the polar region at the lower level and producing the easterlies. However, it cannot explain the westerly in the subtropic, in the extratropics, and therefore we need the three cells, which we have already shown from observations that there exist. And once the three cells are there, then the westerlies are also explained. So everything is fine. But what is not fine is that where does this Farrell cell, which is known as Farrell cell, comes from? This cell is not intuitively explainable because it rises where the surface temperature is low and sinks where surface temperature is high. Because the temperature is maximum at the tropics and systematically decreases towards the polar region. Therefore, here it rises at a surface temperature which is much lower than, and sinks at a surface temperature at a higher level, and therefore this is not a thermally direct cell. Initially, we thought that the one big cell is a thermally direct cell. The hot air goes up, comes down in the polar region. But that is not true. There is another cell which is a thermally indirect cell. What produces a thermally indirect cell? And that has been a major question for a long time. So the middle cell is in ascending motion takes place around 60 degrees, where the surface is relatively warm, and descending motion takes place around 30 degrees, where the surface is relatively surface is relatively cold. I'm sorry, this is a mistake. Surface is cold, and 30 degrees, where the surface is relatively warmer. Is a thermally indirect cell. So this is now called a Farrell cell. William Farrell, an American meteorologist who conceptualized this sometime back in 19th century. So what is responsible for this indirect cell? So let us try to understand that. And so to understand that indirect cell, I need now we have to come back to this the role of the transient eddies. So these cells cannot be understood without mean meridional circulation. The big cells alone cannot explain this indirect cell. So we need to invoke the the Rossby waves and the transient eddies associated with the Rossby waves. And how can they produce? Because as I explained in the beginning, they can transport these heat and momentum across latitudes. And let us try to calculate them from observations. How much heat and momentum these eddies can transport, and can their convergence and divergence of this heat and momentum can give rise to atmospheric motion by these eddies themselves? Can they force motion? And then I'll demonstrate that in fact their convergence and divergence of these momentum and heat by the eddies can force atmospheric motion, and that indirect sail is indeed a result of these transports. First of all, let us see how they transport. To transport this, how they transport, let us understand the nature of these eddies first. The nature of the eddies is essentially, as I mentioned in the beginning, in the first lecture, that let us take one point here, somewhere in the extratropics, and plot the daily winds and the U component of the wind and the V component. So there are very large fluctuations are there. As I mentioned, this weather in the extratropics is very large amplitude, have large amplitude fluctuations. And these fluctuations essentially produces, so deviation, the mean is here, long-term mean is somewhere here, 20 meters per second, but the deviations are also of the order of 20 meters, 15 meters per second. So that is the kind of large amplitude, and the meridional wind fluctuations are also as large as the zonal wind fluctuation, the U wind fluctuation. Normally you see that the mean meridional wind is, if you take a zonal mean, zonal mean means mean around a latitude circle. If I take a latitude circle of the U component of the wind, that is very strong zonal. That is west to east. The meridional wind is very relatively small on average over this, because there is some northward motion in some part and southward motion in some part. Northward, southward motions are there. As a result, on average over this latitude circle, the zonal mean meridional wind is small, but the fluctuation, day-to-day fluctuations are very large for meridional component of the wind also. And this is important. And so let us take a look at the standard deviation of this. Standard deviation will give me an amplitude, a measure of the amplitude of the day-to-day fluctuations of the winds at different levels. At the surface level, at 850 millibar, 500 millibar, 200 millibar, and so on. So if we do that, okay, so before doing that, I'm just showing you a standard deviation of the winds, of zonal winds, U component of the winds at 200 millibar. Standard deviation is calculated over a period of this is winter months, I suppose. During a period of season. In that season, what is the fluctuation? What is the amplitude of fluctuation? If I plot that at a very great point, what is seen here is a very large standard deviation in the middle latitude and very small standard deviation in the tropics. And this is a very important recognition that is very important, because we keep thinking that the tropical weather is very strong. The fluctuations of the wind in the tropics is very small compared to the fluctuations of the wind in the extratropics. The extratropic weather is much more vigorous. In tropics, we have a vigorous weather once in a while, but they don't continue every day after day. But here in the extratropics, the weather continues, repeats, very frequently. As a result, over the season, there is large amplitude fluctuations of winds, and this is an important part of our climate. Actually, we'll see that. But suppose now I put the standard deviation of U wind as a function of height and latitude. What I see is the tropics is, of course, is rather weak. And these are 2 meters per second, 3 meters per second, and the upper atmosphere maybe 6 meters per second. But in the extratropics, we have wind fluctuations of the order of At the surface itself is like 6 meters per second, but at the upper air, it is like 12 meters per second. In the one hemisphere, maybe 16 meters per second in the other hemisphere. The winter hemisphere has a larger fluctuations compared to the summer hemisphere. And this, so now you go to the meridional wind. This is also, no, this is in the summer hemisphere, in the summer season. So this is winter season, northern hemispheric winter, northern hemispheric summer, in the southern hemispheric winter. So this is now stronger here. This is now relatively weaker, but now it becomes comparable because on the other hand, now if you go to meridional wind, the V component also equally strong. So this is what makes this the V component of the wind can then affect this transport across latitude, because there are large fluctuations, there are large amplitude fluctuations, they're not very small. And that is as large as 15 meters per second fluctuations from day to day is there. And of course, that is probably standard deviation. Sometimes they could be twice as large with some weather events, strong weather events. So this is important that we need to remember. So in summer also, it is very slight seasonality, but the fact is that the upper atmospheric, the transport, the fluctuations of day-to-day fluctuations of the winds in the extratropics are about 4 to 5 times larger than that over the tropics. And so this is important characteristics of our weather. Now, if we go back to now calculate those transports, I considered, take the data from now observed data. Every day we have this data. From this daily data, I can find out the values of the transients. You remove the long-term mean, and therefore you have the seasonal mean. So therefore you have day-to-day fluctuation transients, transient eddies in the U and V, and then you do a product of those, and then average over the whole over the season. And then you average over each of the latitude circle. So this is the zonal mean. So once you do that, so this gives me the meridional transport of U momentum, zonal momentum, by the transient eddies at each latitude and with different heights. I have now plotted that over the whole as a summary here. Now, what it shows is that, so therefore, these transports will mean that if it is positive means northward, negative means southward. Okay. So what it means is that a positive transport in the northern hemisphere means towards North Pole. Negative transport in the southern hemisphere means towards South Pole. So it means the transient eddies are affecting the transport of zonal momentum towards pole on both hemispheres. And this is something that is happening in the observations. So that is observation, the wind, the fluctuations are managing a transport of energy, a transport of momentum. Of course, there is some equatorial momentum in the polar region. So there will be some kind of a convergence of momentum in this region. There will be convergence of momentum in this region. I'll talk about that in a minute. But then, now how do they actually transport these? So let me just. So how basically these waves, how do they actually make this transport happen? This can happen because of the shape of the waves. For example, this schematic shows that the waves are essentially sort of tilted, and they are non-linear. The troughs and ridges are not sinusoidal, and then here in this region is cold and this region is hot. So now this the cold air comes through this. When this wave is producing this kind of a motion, the cold air comes from this side. So here your meridional velocity is southward, and it is bringing temperature which is colder than normal. That is also negative perturbation from the so temperature. The T prime is so in the hot region, the hot region, the V prime is positive northward, and the temperature is also positive because it is bringing hot air. So this is V prime, T prime is positive here, but here when the southward motion, it is bringing cold air, so V prime is negative and T prime is also negative. So the negative also produces positive transport. Therefore, over a period, over a wavelength, the wave can actually produce a transport towards north. And similar thing happen in the south. So for this is, that is for temperature, and this is for wind also. It's same thing happens, because here the V prime is negative and U prime is also easterly, therefore this is negative. This is V prime is positive, U prime is also westerly, therefore it is positive. So both adds to northward transport of momentum, and therefore the waves, because of their structural nature, can produce these kind of a northward transport. And as a result of that, you can actually and produce some sort of a convergence of this momentum in this region and this region. I'll come back to that in a quantitative manner in a few minutes. Now, I have not shown the temperature. The calculation of the same thing can be done from observations using the temperature perturbations and the momentum perturbation and the meridional wind perturbations. And if you calculate the heat transport by the transient eddies and do that over decision and then average it over the whole latitude circle, we get the temperature transport, heat transport by the transient eddies is like this. And they are instead of they are again negative to the in the southern hemisphere and positive in the northern hemisphere. So this means that there is poleward transport of heat as well in both hemispheres by these transient eddies. So this is very important. Of course, the structure is because of the because of the temperature perturbations are different, because temperature perturbations can be as large in the surface and the largest in the surface also, but the wind perturbations near the surface due to friction are small, and therefore the transports near the surface by the wind is small, but it can be large for temperatures but as well. Therefore, the vertical structure of temperature transport is somewhat different compared to the momentum transport. But the main point is that both heat and momentum are transported poleward by the transient eddies, and that is important part for our. So this is in the summer and this is in the another season. But same, it doesn't change very much except quantitatively little bit. So how does this affect the mean temperatures? So it essentially what happens if you look at the zonal mean temperature in the steady state. Suppose on a seasonal mean, the temperature is not changing, and therefore then the vertical velocity is essentially given by these quantities, which are essentially the convergence and the divergence of the heat energy by the eddies plus the radiative cooling or the latent heat energy. So this can also affect, but in the polar in the extratropics, this radiative balance is rather cooling the atmosphere, and there is not much of a latent heat going on. Therefore, this is what is a dominant term in the extratropics, and that can be seen from these calculations. This is the kind of from those data itself, I have calculated what is this momentum divergence by the eddies, and the heat divergence by the eddies as a function of latitude and height, and the Q perturbation. This is the latent heating perturbation. That is large only in the tropics, But in the extratropics, it is just basically radiative cooling. And so if you put this all into in a simple equation, you can actually and determine that the heat convergence. So there is heat convergence in this region. So heat convergence means there is a lot of heat is accumulating in that column. That heat convergence over the whole column makes the vertical velocity going up. And that is what produces that at 60 degrees, where there is the surface temperature is low, but the atmosphere, there is a lot of convergence of heat, and that convergence of heat makes the column lighter, therefore makes the vertical motion over there. That is what it drives the Ferrel shell. And there is heat divergence to this side, and that produces the sort of Ferrel shell in this region. And that is the main, and this is consistent with the momentum convergence, which will produce the necessary meridional velocities at the top and the bottom. And that is how schematically we can show that this heat convergence will give rise to this kind of a upward motion around 60 degrees and downward motion here at 30 degrees. And the momentum convergence will give you surface motion towards the pole and upper air motion towards the equator. This will give rise to an indirect shell. And that is how we can actually understand and that is the origin of the indirect shell. So I think I'll quickly go through a couple of so if we actually look at the vertically integrated energy transport across different latitudes here. So now that I have shown a vertical distribution, but suppose I integrate vertically and look at basically over the whole latitude belt, and that this is the total energy transport. Now the meridional velocity and the total energy, which has these different components, heat and the potential energy also I can add into this internal energy. And that will show this positive in the northern hemisphere and negative in the southern hemisphere. And that is the poleward transport to this in the southern hemisphere, again the poleward transport in the northern hemisphere, and seasonal variations are there. But this is a total amount of energy that is in some units, let us say. We can actually have same units. Now, if I do, what is the energy that is transported by the eddies, vertically integrated, also shows that in the extratropics, it is dominated by the eddies. So the whole part of this transport of the total energy in the extratropics is largely dominated by the eddies in both hemispheres, but not in the tropics, in the equatorial region. In the equatorial region, the eddies do not produce much of a transport, and that is produced by largely the mean meridional circulation. In the equator, there is this Hadley circulation. We have the Hadley circulation is the mean meridional circulation. These are weak, and therefore we have these annual mean. It is small, but the seasonal cycle is very large because the Hadley circulation has a big changes from one season to another season, and that is therefore in the tropics the mean meridional circulation is important. We cannot do without it. But in the extratropics, you can the mean meridional circulation is a small. The Ferrel shell does not transport a whole lot of energy, but as much as the eddies, the transient eddies do. So therefore, we need both meridional circulation as well as the eddies to achieve the total transport of heat and momentum. So you can calculate these as a function of latitude, the whole energy transported by the atmosphere, and the amount of energy that is required to be transported as a forcing from the top of the atmosphere. So at the top of the atmosphere, we had this balance, right? You remember? This balance here. So if I had calculated these at every latitude, that much energy is required to be transported. Has the atmosphere achieved that? And that amount, that curve is here. That curve is, sorry, I should have put it back. So that curve is here. This curve is what is, So that energy balance at the top of the, I mean, that is the total energy that is being accumulated in the tropics and lost in the polar region. And if I have to maintain the equilibrium temperature, how much energy I have to transport across each latitude, that I can calculate from that equation. And if I calculate that, and this is how much energy I need to transport. And now from the observations, actually, I am calculating how much we are calculating, and that we get it here, atmosphere. And the atmosphere does not achieve completely how much the amount that is required by to be transported by the energy, the forcing at the top of the atmosphere, the energy constraints. So the rest of the energy then it has to be actually transported by the ocean. So ocean also participates in the energy transports and achieve the equilibrium by transporting a certain amount of energy. I must say that this particular figure is a little bit old, and this estimate by atmosphere is now revised. It is much more than this, a little more than this, but the ocean transport is still required to achieve the balance. Unfortunately, ocean we don't have any data I mean almost no data to make the kind of calculation you can do in the atmosphere. In the atmosphere we have now pretty good data. But ocean we don't have. We're beginning to have better data now in the ocean, but ocean then combine the data that is available and use a good model, ocean model, tries to do estimate of the energy transport by the ocean at these, and that tends to be more or less indicated the kind of the difference that we need to achieve the required energy balance. Okay. So with that, let me go back to, so how is this energy maintained? So this is, I think, E for our, that basically the atmosphere, the solar energy is what drives our atmosphere. Okay, motions in the atmosphere. It produces the equator to pole temperature gradient. So this produces dt dy. So the equator goes up, temperature in the tropics goes up, polar region temperature goes down. So temperature gradient is produced, a huge temperature gradient. Now the temperature gradient has a lot of potential energy now. This cannot be stable. So it becomes unstable at some point of time. It produces through that thermal wind relationship, it produces a vertical shear of the wind. Vertical shear of the wind, is susceptible to hydrodynamic instability. And those hydrodynamic instabilities are the Rossby waves. And those Rossby waves then, I call it baroclinic instability. That baroclinic instability then produces Rossby waves. Those Rossby waves then transport heat and momentum poleward. And then once the heat and momentum is transported poleward, the temperature gradient is reduced. So temperature troposphere, I mean, tropic goes up and polar region comes up. So temperature gradient is reduced to an extent where the vertical shear will be reduced, and therefore winds, the instability might also be quenched. And then, of course, the solar radiation is still putting more energy in the tropics and more taking away energy from the in the polar region. Therefore, once the transport stops, then the solar radiation will further bring the temperature up in the tropics and bring it down in the polar region. Again, the whole cycle will repeat. And this is how it is going on. And so our climate is always in a non-equilibrium. And this is kind of a dynamic equilibrium where the radiation balance drives the circulation and the transport energy, brings it to an equilibrium. Then again the energy balance drives this temperature gradient larger, temperature gradient become unstable. And then again the waves become stronger, and then again the transport takes place, and things go on. And that is how. So therefore, this is where the complexity I think I talk about. So there's a chaotic weather and the mean circulation is coexist in climate, and they cannot do without each other. The weather disturbances are instabilities of the mean flow, and then but then they transport energy and kill the mean flow, and therefore change the mean flow, in a way kill the instability. So therefore, neither the weather disturbances nor the mean can exist without each other. So therefore, this is the complexity of our system, and I think this is similar to something that happens in many other physical systems. So with that, I think I'll stop here today. Just 1 minute. Let me. So in fact, this importance of this eddies, before I go, before I stop, maybe I'll just mention about this importance of this mean meridional circulation and this eddies. So these waves are a very, very important part of it. In the late 40s and early 50s, there is a big debate going on about the importance of whether it is general circulation and the climate should be is determined by the mean meridional circulation or by the eddies. There are two groups of two schools. One with Rosby and Victor Starr and others, and then who thought that general mean meridional circulation is the and then there is a group of Starr, Pullman, and then there is a group by which Pullman and Riehl and Nemias, and then this group thought that the eddies are more important. So there was a huge debate that went on, sort of very interesting emotional debate in some 1948 or 50, and in the issue of Journal of Meteorology, which is now the Journal of Atmospheric Science, there is a huge debate between these. So in response to an article by Victor Starr, Rusby and Starr, Pullman wrote in this Journal of Meteorology. It is not clear whether the authors intended to question the. So very, very interesting, very interesting, very. And then he went on to listen to the second. I would like you to read. So then Victor Starr wrote back. Apparently, Pullman suspect me of highest hearsay, lest I suggest energy production process, etc., something. And then he goes on to say that indeed, if such fruits of hearsay, then I say let's have more hearsay. so the Pullman speaks of the whole foundation of dynamic meteorology. What does he mean by it? And I certainly doesn't mean the whole collection of Sandry differential equation. So this is like a very personal debate. So this debate went on, but I think this debate has not. This is no longer a debate. We now know much better. But at that point of time, the data was less, and there are still this. So this was a very important debate, and then it sort of became much clearer now. But I think this is the important aspect of how the general circulation on climate maintains itself. So with that, I'll stop today. And so I must say before I leave, just I said that I have given a list of references that probably will be uploaded later on. I must thank one interesting. There is a book called Theory, General Circulation, Theory, Modeling and Observation. This is the proceedings of a workshop. It was in 1990 odd some year. Okay, it's NCAR colloquium. This book influenced me, and there was an article by Mike Wallace, and this was a beautiful article. And on that basis, most of my sort of narrative has come from that. So I want to thank him for and this book is available online today because now it is. I'd suggest that if anybody wants to learn some of the sort of history of this and how things of most of the important things. This is about early 90s. That time itself, most about things actually we knew. And many other aspects of general circulation are discussed in there, which is a very nice book. Of course, this book by Ed Lawrence is a very beautiful book. It is also available freely today, I think, in the online. It's a beautifully written book. Many of the things that I have discussed here are taken from some of the figures. I have generated them myself, but figures, the concepts are there from this book of. This is a book, of course, is a detailed book about various different climate. It's physics of a very big book. It's a very good research material.